regularization, and kernels. Okay, so what is semi-supervised learning? Only semi-supervised. Okay, so what are we going to do today? We're going to motivate semi-supervised learning. We'll discuss what graph-based semi-supervised learning. A key concept to understand how it works, why it works, will be the norm and the cut of a graph labeling, which in some sense is a measure of the complexity of your classifier. We'll discuss the minimum cut method introduced by Blum and Chawla in 2001, which really spawned this area in machine learning. We'll discuss the Laplacian method in its most, I'd say, vanilla form, which is probably what most graph-based semi-supervised learning is based on. There's many variants, and that's quite successful. And then we'll kind of put things together a little bit and talk about how to view the minimum cut method and the Laplacian method within one framework, which is a P-Laplacian. Also, we'll try to understand why the Laplacian works a little bit. We'll try to give some perhaps informal arguments. The key to understanding it is just the norm and the cut kind of measures the complexity of a classifier. The effective resistance kind of measures the distance of two input points in the space, and that will help us perhaps get some feel for why the Laplacian-based method works. There's notes over there. Okay. There's other references, of course, but it's a very nice downloadable ebook called Introduction to Semi-Supervised Learning by Zhao Zhenju and Andrew Goldberg. Zhao Zhenju done very much important research here. Chapters 1 and 2 are a basic overview. 5 we'll go into more detail on most of what I do today, at least the first 5 bullets. And I think you can just get the PDF off of the internet. Otherwise, you can go through the library website to pick it up. Okay, so let's understand the motivation for semi-supervised learning. Okay. So semi-supervised learning, I think the key idea of when it's going to be successful is that somehow you want to exploit the structure of the input space to improve learning, where the input space, we think of our learning problems as having inputs x values and outputs y values. The input space is the x's. So suppose I give you this following learning problem. I have 2 class learning problems that we'll talk about today. One class is always labeled +1, the other class is always labeled -1. How might you, what would be a reasonable label for this point, and how would you justify that label? There's copies of notes here. Maybe I can put a little chair over there. Notes are here now. Okay, so we have the plus point, we have the minus point. You're all expert machine learners by now. How might you go ahead and label it, and give me a reason why you might want to choose that as a label?
Plus, minimum distance to plus.
Yeah, that seems like a reasonable hypothesis. You know, why not label it plus? Because we see it's the minimum distance to plus. And thinking about last week's SVM lectures, you might go, oh, wait a minute, we could find the optimal separating hyperplane. I know that, SVMs are really good. So, okay, this is a hyperplane. Yes, I've maximized the margin between there, and I have to label the same thing. Well, it turns out in the 2-point case, optimal separating hyperplane is going to label the thing the same as the nearest point. So it makes sense, given only these 2 points, to label this as plus. Okay. Semi-supervised learning, you want to take advantage of the unlabeled data. You can't take advantage of something without making assumptions. And there's different assumptions that try to explain why various semi-supervised learning methods make sense. 2 common assumptions are the following: that we can use semi-supervised learning to do well in the following sense. If points are kind of in a cluster, whatever a cluster should be, well then it makes sense to label them the same. And maybe if the unlabeled data forms clusters, maybe we should be guided a little bit by the unlabeled data in a smooth fashion. Another perspective, which I'm not going to emphasize at all today, but I'm going to put it up for those of you who are quite mathematically inclined, is the idea that we have data lies in some very high dimensional space, and if we try to estimate the function in this high dimensional space, we have this problem with the curse of dimensionality. Basically, the more points we have, the more dimensions we have, the rate at which we can estimate things is somehow and generally gets worse as the exponent of the dimension. So things get quite large in high dimensions. But the idea of the manifold is, the ambient space, the number of inputs, like when we scan the digits and we might have 1,000 by 1,024 pixels, this might be a million dimensional representation. But the idea is that even though the representation might be very high dimensional, maybe that manifold of images, that we can find some sort of space within there up to some noise that's much lower dimensional. And so then if we're trying to estimate things, we should estimate things relative to that lower dimensional space. Justifying this, arguing for this is quite mathematically demanding. I'm not going to attempt that. Basically, the story that we want to tell about semi-supervised learning today is that points which are similar are in the same cluster. Okay, so that's if you see 2 points. Now suddenly I changed the data to look like this. Now how might you be tempted to label the question mark point? Leading example, just play along with me. Let me lead you and then make fun of you and do all those terrible tricks that lecturers do. Oh, you're a tough class. So how should, why might we, what now might we relabel if we're going to change our mind and not label it as plus? And what might be a justification for choosing that as our labeling?
Minus.
Excellent. I see that a student is definitely going to get a distinction on the exam. And somebody else tell me why minus. Yes?
Because it's not plus.
Yes, that's right. I told you plus is wrong. But if you ignore me and you just, what story could you want to tell your boss, this is a minus. Why is it a minus, worker drone? Well, it's a minus because...
If you apply the same algorithm starting at the red minus, it will filter through the whole tower.
Yeah, maybe you think that these things are all clumped together and we have 2 clusters, there's a lot of apparent space between them. So if somehow the data respects these clusters, maybe we want to label it as minus. Okay? So we'll look at a method today which will have exactly that property and try to understand that method. Okay. So let's go back to the same thing. Well, maybe those don't look like Gaussian, but let's think about the setup for a little bit. imagine we have two Gaussian distributions, okay? We have a Gaussian here and a Gaussian there. And these Gaussians are generating points, blah, 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 blah. You know, I don't know how they're generating points, they're just generating points. And then there's some hyperplane, like this, okay? Now this hyperplane, you know, maybe, you know, this is like people who are going to be apt to ski well, and on the other side of the hyperplane are people who aren't going to be apt to ski well, and the x's are the people being generated by these Gaussians. Now, suppose we have known, think about it for a moment, suppose, so here's our Gaussians, let's maybe draw a picture. You know, we have one Gaussian kind of, you know, maybe it's kind of elliptical shape and it's generating some points here. Then we have another Gaussian, maybe generating points here. And then there's some hyperplane, and this hyperplane is going to pass through these two Gaussians. Like that. Okay? And so that means the points on the top here will be labeled plus. And the points on the bottom here will be labeled minus. And suppose, in addition to getting labeled data, we can somehow generate a lot of unlabeled data. Will the unlabeled data help us very much in this scenario? Sorry, I keep moving it around. How will the unlabeled data help us, or will it not help us in this scenario? We can get a whole bunch more labeled points. Much more unlabeled points. And we don't obviously know the hyperplane in advance. If we knew the hyperplane in advance, we'd have no learning problem.
Well, unlabeled data can help us in any case to figure out the parameters of the distributions better.
Yeah, it'll help us figure out the parameters of the distribution, but will it help us predict the y values of the... We have the two Gaussians generating our points, and then we use this hyperplane somehow chosen arbitrarily to label the data, where everything above the data on one side is plus and everything below the data, below the hyperplane is minus.
No, it won't.
Yeah, I mean, I tend to agree with you. I mean, I can't, there's no necessary connection between the hyperplane and the unlabeled data. Somebody hands me these two Gaussians, I know the parameters exactly. Can I somehow use that information to make a better prediction of the y values? No. But now let's consider the other scenario. Suppose we know something about the learning setup of the problem. You know, sometimes maybe the data, the distribution of the x values has nothing at all to do with the y values in particular. Like in this instance, you know, you have some random distribution, but then the thing which you're labeling doesn't kind of depend on that distribution. But instead, we say that the hyperplane is known to separate the centers of the Gaussian. So maybe this is one center, and maybe this is the other center. If we know the hyperplane separates, so everything over here is labeled minus, and everything over here is labeled plus. Can we use unlabeled data to help us? Yeah, I think we can use unlabeled data to help us because, you know, we might have just, suppose we only had a few labeled points, you know, our knowledge of where the Gaussians are would be kind of weak. But if we knew the centers of the Gaussian exactly, then for instance we could, and the variance of these Gaussians, we could use this to get an estimate of exactly what the label is because our hyperplane separates them. So, yes.
You're saying it separates them in some sort of ideal way, or just it separates the centers?
Well, here I've imagined it separates the centers.
But as well as possible, like in a sort of hyperplane.
Yeah, imagine that this center, that I found the mean between them,
Right.
and then I've made it perpendicular to. But you know, even if it separated them in some weak way, probably with enough data and sufficient assumptions, any sort of assumption on separation, you can probably turn into something that would help you predict with more unlabeled data. So here we can see a scenario where unlabeled data can help and a scenario where unlabeled data can't help. Okay. You know, unlabeled data, who cares? Why are we making our life difficult? Why don't we just use labeled data? The problem is realistically for many problems, gee, the top of the slide is always cut off. Sorry, it doesn't say that much. Unlabeled data, in some sense, is maybe much cheaper to get than labeled data. You know, imagine we have some news stories, and we want to know if these news stories are about the Russian economy, and somebody hasn't labeled all these news stories. It's going to be perhaps non-trivial to get labels. You know, you're going to have somebody read the news stories if you want real accurate labels. That we're going to then use for a learner to learn about, to tell whether the stories are about the Russian economy or not. Or imagine voice, for instance. You know, we know Google Voice, you make a phone call in the US, or Siri and Apple, they have tons and tons of your voice data. They're getting more of your voice data all the time. They have lots of collected voice. But how much of this voice data is labeled? Probably not a lot of it's labeled. You know, it's going to take many hours to transcribe voice, and especially if you imagine, you know, you have crowded conversations in a room, and you're trying to identify individual speakers. You can get lots of data like that, but lots of unlabeled data of that nature. But labeling is going to be hard. We have some experiment where we want to design a drug. We may be able to generate many sample molecules and get a whole lot of information about a variety of sample molecules, but for some specific property, which is what we're actually interested in, this is effective against some disease, for instance. You know, lab work and experiment may be, for each individual molecule that you choose, may take months of time. Let's leave it at those examples. Okay. So you've done some supervised learning. So recall the typical goal of supervised learning. Here we're given some set of data. These are x values. These are our patterns. Often they're vectors, and Rn x's are. And y's are our target values. And our goal is to infer some function such that f of x is approximately y in future data. So for classification, we perhaps y is -1 or +1, maybe regression to smooth value. You've learned about support vector machines. You've learned about linear regression, and many such algorithms will produce functions for you. I don't know if you're recalling unsupervised learning. I guess some of you are probably taking unsupervised learning in the class. Unsupervised learning is perhaps often more diverse in some ways than supervised learning. So it's hard for me to give the exact goal, but the typical goal is you're given some patterns. Now you're given where these are x values, and you want to model the data in some sense, whatever model might mean. So for instance, clustering, you want to find some partition or function on the data such that you divide the data into, for instance, separate clusters. Maybe you want to reduce the dimensionality of your data in various ways to feed it into another learning algorithm. Well, then you can use, for instance, PCA. Okay. Semi-supervised learning. Well, supervised learning is good, unsupervised learning is good. Let's combine them. Have something better. So we're given the data. We're given a data sequence. We're given some L labeled values, x1 through YL, and that should be an L plus 1 on the slide, and an L plus n. XL plus 1 to xn are the unlabeled values. And our goal is to infer some function now, such that f of xy is approximately yi. We're going to go into that in a little more detail in a moment. There's a distinction we'll want to make. But the idea here is to combine supervised and unsupervised learning. Lots of different techniques for it. Today, we're going to only do graph-based semi-supervised learning. It perhaps fits very nicely with randomization and support vector machines. Questions so far? Okay. Let's point out some other, just for a moment, some other natural ways that you might do semi-supervised learning that are kind of common wrapper methods, because maybe it's just something immediate, easy that you could try at some point. So one standard technique of maybe doing semi-supervised learning would be bootstrapping, where the idea would be is you have your labeled data and your unlabeled data. So you're like, well, how can I use my unlabeled data with any supervised technique? Well, one thing which you could do, for instance, would be to learn a function on your labeled data, use that to predict labels on your unlabeled data, then combine those hallucinated or predicted labels with your unlabeled data and your original data and use that to predict. Something one can try. It can go badly wrong sometimes, you know. But bootstrapping is a natural thing that people try. Another thing is, if you have any sort of clustering technique, you have some method that's already putting your data in clusters where you can use your unlabeled data to build clusters and then simply use your labels to vote on those clusters. So these are simple techniques which are certainly worthwhile trying on any problem, because in some sense they're trivial to implement. They can often go badly wrong, and they're harder to perhaps analyze than some of these other methods that we've discussed. But those are quick and dirty methods. Okay. A distinction we want to make today. So there's inductive and transductive semi-supervised learning. So induction, we have the same model. We have a training sample, xi, yi, and we have our unlabeled data. And our goal is to learn a data on some future sample that perhaps has nothing to do with your given training sample. Somehow you want to infer a function for every possible x. Transduction, instead what we have is we have a we just want to predict on this unlabeled data set. We don't want to predict any further. We're given a finite set of objects. We're given labels of some of those objects, and we want to predict only on those. In some sense, this is a simpler scenario than the other. But on the other hand, you can kind of, if one wanted to prove things about it, you can perhaps prove stronger things about transduction since you're making a stronger assumption. So let's look at graph-based semi-supervised learning. Let's look at some examples of graphs. Here's a graph built from the USPS digit data set. These are built by scan digits, and we built some graph by using a k nearest neighbors metric to connect each point to its 3 nearest neighbors. The other is a random graph, which we've used for some simulation experiments. Graphs we haven't actually used, but other people have used. Here's a network from bioinformatics of these proteins and how they interact. The other is one representation of a number of internet posts. I guess we've actually done some experiments on. I've done a certain amount of work on web spam. Here the problem is detecting whether a website is spam, i.e. somehow it's not really, either it contains malware or it's just there as for search engine optimization. There's a lot of companies interested in this, done some joint MSc projects here with Cisco on detecting web spam. You know, these data sets for web spam start getting very large. We start having collections over 1 million websites. I would like to do some experiments with the Twitter data, but I never have. Certainly other people have, and at UCL here, there's a group in Bristol that's working with Twitter. At UCL, we do have access to this data. Phil Trelevin and Robert Smith have a project where they collect the Twitter data for various analysis issues. Okay. So we're doing graph-based semi-supervised learning. I gave some example graphs. Where did the graphs come from? Well, some of these, they are perhaps intrinsic, like, you know, with protein, maybe, you know, there's only certain proteins that another protein will interact with. You can build a graph with edges such that they interact. Social network, you know, Facebook, you can build a graph via the friend relationship. Twitter, similar. Email network, we use an email to citation network, and so forth. But commonly, often semi-supervised learning is not concerned with these intrinsic graphs, but graphs that you build from a given data set. Let me kind of describe how these methods work. So the idea of building a graph from the data set is somehow we want to build a graph that captures the structure of the data. And so key thing we need in some sense is some way of knowing how near 2 data points are to one another. So we have some sort of metric or distance between 2 points and everything. And it doesn't actually have to be a metric. It just has to be some measure that tells us how similar or how distant 2 things are. So for example, you can imagine doing document classification and you want a very simple metric on how similar 2 documents are. Well, you could, for instance, count how many words they have in common. You know, perhaps you want to refine that in some fashion, but at first glance, you know, you could perhaps, you have documents, you could put a similarity there by counting the words in common. Okay, so to build these graphs, let's consider 3 different ways. First, we have the k nearest neighbors method. So for k and n, which is not related to, it's related, but it's different than k and n classification. The way we build a k and n graph is the following. So all the graphs we build today are undirected graphs in the computer science sense. So a graph is, can you read, is this too faint?
Yeah.
So a graph is specified by a set of vertices and edges which join two vertices. And for us, it's an undirected graph, so we have an edge between vertex 1 and vertex 2. That means we have an edge between vertex 2 and vertex 1. K&N graph, we have some set of points. Let's say these are our points. For us, the distance between the points will be roughly the distance that we see on the board. So the K&N graph, let's say we built a 2NN graph on these points. The idea is for every point now, we connect it to its two nearest neighbors at a minimum. So for instance, this point, this is near that point, and it's near that point. Now let's say we moved on to this point. This point's two nearest neighbors are probably here and here. This point's two nearest neighbors are probably this and this. This point's two nearest neighbors are perhaps this and that. So it's not necessarily reflexive. This point's two nearest neighbors are probably this and that. And this point's two nearest neighbors are probably this and that. Now all these double lines I simply remove. And so every point has at least two neighbors to it in the graph, but some points may have more.
You may end up with disconnected graphs.
You certainly may end up with a disconnected graph from doing this. So, you know, there's various ways that you can resolve that scenario. Either you tolerate disconnected components, or you have some other rule. Commonly, people often just try upping K. Okay. Epsilon Ball. Look this up. So Epsilon Ball, we have a set of points. And now we have some distance, let's say it's epsilon. So epsilon is roughly that distance. And every point gets connected to every other point within epsilon to it. So this point would, for instance, be connected to here and here. This point would be connected to here. This point isn't connected to anybody if epsilon is my distance. This point is connected to here. This point is connected to here. As I increase epsilon, it's clear that this will get more and more connected. Okay? We won't focus on them today, but there's various ways of building a tree in the computer science sense on a graph. Here, a typical tree you might build would be a minimum spanning tree or a shortest paths tree. These have the advantage that the graph you create is extremely sparse, and because of its tree structure, you often can do specialized inference algorithms to make computation quicker, which actually ends up being quite important for semi-supervised learning, because the methods tend to be slightly slower than other supervised techniques. So for instance, when we've done experiments on web spam data, to really scale up to sizes well over 100,000, rather than building graphs, we tended to build trees and used collections of trees to predict. Okay. Another common thing to do is to put weights on the edges. So now we somehow weight this distance function, and so for instance now we put some weight on this edge, which would be equal to, if this was vertex 1 and this was vertex 2, perhaps e, where we have e to the see the distance between 1 and 2. So the farther points are apart, we have a negative exponential here, the smaller the weight. Often a weighted graph is combined with one of these other techniques, like K nearest neighbors or Epsilon balls. One reason being that if you build a graph that doesn't have many edges, some of the inference techniques for inferring the labeling are faster, so the sparser the graph, the sparser you can infer on, and sometimes you might want to use some of that weight information. Sorry about that. Okay, questions so far?
Could you show how to do a tree based, maybe as an example for it with a couple of points?
Sure. So let's take a look at a minimum spanning tree. So minimum spanning tree is quite good in practice, tends to be a little better than the shortest path tree. So now we have our points. Let's say our points are A, B, C, D, and E. We have a set of distances between them. Now, each of these distances, so on each edge we have some distance dij. Minimum spanning tree of a graph is equal to the argmin of all trees in the graph such that the sum of the distances on all the edges in the tree is minimized. Okay, so imagine that we have, this distance is 20, this distance is 1, this distance is 4, this distance is 5, this distance is 6, this is 9, this is 10. What we're doing is we're finding a tree for instance, maybe here's a tree. Such that if we take all the distances on the edges, here 8, 4, 5, and 20, the sum of those distances is minimized. How do you do that? You make me think about it. I can probably recall, but I mean, I can tell you how to do it, but I'm worried that it's too far. You can use Dijkstra's algorithm or Kruskal's algorithm. I'll wave my hands about how to do it, but surprisingly, finding a minimum cost tree is an example of something that you can find quickly. It's roughly not much worse in complexity than the number of edges in your graph. To find it, for instance, you start with an arbitrary vertex, okay? And then you say, well, what's the nearest vertex to that vertex? now I have I have a tree-like structure with two vertices in it. Then I can ask myself, what's the next vertex that I can choose such I still have a tree-like structure that has minimum cost? And I can follow in that greedy fashion and build a tree. And there's other algorithms based on similar principles that will build a minimum spanning tree. Okay. This is, in comparison, for those of you who are taking evolutionary computation, you might want to build a Hamiltonian cycle on a graph, and now you have another path-like structure that's very expensive to compute. A shortest path tree, sorry, I actually like this stuff, so I'm glad you asked the question. So I enjoy minimum spanning trees and shortest path trees. Shortest path tree is we choose a vertex, and now we consider what's the shortest path from that vertex to every other edge on the graph. It turns out that if you look at the paths that make up the shortest paths to every other vertex on the graph, that these paths form a tree-like structure. And you can also find this efficiently. So the shortest path tree, if you're taking a single vertex, is giving you an extremely good local approximation of the distances around that vertex. But it's not really a global approximation, whereas a minimum spanning tree, if you're kind of thinking about how it's approximating the graph, it's giving you a global approximation to the distances. I can give you another reference if you ask me during break. Okay? Other questions? Okay, so we have various ways that we can build graphs. And then once we have these graphs, we're going to want to use them in our semi-supervised method, in which there's going to be a variety. In terms of actual popularity and what people do, if I just want to do something quickly, k-nearest neighbors tends to always work fairly well if any of them are going to work well. Epsilon Ball, you might be able to prove some things about it, and might be elegant in some ways, is actually very hard to get to work on many data sets. Weighted graph, k-nearest neighbor tend to work a little bit better. Somehow it makes the data more ordinal, and it often tends to work. But if you have time to tune parameters, i.e. you have a weighted graph of k-nearest neighbors, well, you have two parameters to tune, so it includes either one as a special case. And so if you have a large enough graph and enough labeled points and your unlabeled data points, then the combo method will be most likely the best for you. Okay. Let's go forward a slide before we do this. Okay, before we discuss the complexity of the linear graph, let's recall some stuff that we've already done with Massey. So Massey discussed already regularization, where the key idea of regularization is the following. You have some form of complexity. You know, in general, for many linear algebra techniques, that complexity is going to look like a square norm. That's not always going to be the case. And what we want to do is we want to then choose some predictor, f star, which minimizes the error. We want to choose a predictor f that minimizes the error on the training data plus the complexity term. Where the motivation being is, you know, if we don't have any complexity at all, and we fit the training data exactly, well, we're maybe in some sense fitting the noise. If all we care about is complexity, well, we have no predictive power. So regularization is generally this idea of trading off the minimization of error and complexity. So you saw an example of it, support vector machines and ridge regression, where in ridge regression you have the square error, and you could either choose the predictor with minimal norm, but you might say, well, I might be a little overconfident choosing that, and I regularize that with the squared norm, and I instead minimize this objective. When you considered spaces with kernels, for instance, if you used a Gaussian kernel, or if you use a Gaussian kernel, as long as you have consistent data, you can interpolate, you can fit every possible function, then it really makes sense to regularize. You pay something based on the complexity of the function you're fitting your data with. Okay. So just on a support vector machine, here you would have a hinge loss term, for instance, and here you would have the norm induced by the kernel space, and you'd be fitting a function. Okay. Okay. So if you think about, before thinking about graphs for a moment, if you think about a function in Rn which you're fitting with some kernel, like a polynomial kernel or a Gaussian kernel, the regularization term is enforcing some sort of smoothness on this real valued function. It's basically, depending on the kernel you choose, it does it differently, but in Rn the picture is always the same to some degree with slight variance for most kinds of kernels. Is you're avoiding spikiness in your fit. You're enforcing smoothness. The derivatives aren't too sharp. If your function suddenly goes up and down, that's going to raise the norm of your kernel, and that regularization term is going to go up. So in Rn, you're fitting a smooth function. So now, if our idea is that we want to fit some labeling on a graph, we need some notion of smoothness of our labeling. So let's forget about real values for a moment, and we think about discrete values. A real natural way to perhaps measure smoothness is this idea of the cut on a graph. Okay? So here I have a graph consisting of some 10 vertices and however many edges, and the edges that I've marked in red correspond to cut edges, i.e. there's a disagreeing label between them. So here I disagree, there I disagree, there I disagree. And if I look at that graph, I might think to myself, oh, those two halves kind of naturally fall into two separate clusters. So this, in some sense, is a relatively simple labeling of this graph. This, on the other hand, may look like a fairly complex labeling of the graph. The pluses and minuses are quite intermixed. If you're at some given point, it doesn't seem to necessarily tell you anything about what's true locally by it. And if we count the number of cut edges, the only edge that isn't cut here is this edge. We see that the number of cut edges is 12. So in the discrete world, the labeling that we want to use is just the complexity is the number of cut edges. Okay? But because we want to do things not just in the discrete world, the continuous world leads to nice, smooth optimization algorithms, we want our complexity to not just correspond to labeling u minus 1 and plus 1, but we're going to do something like with SVMs. We allow our labeling vector to be some value in Rn, whereas, you know, if it's large and positive, we're quite confident that it's one class, and if it's large and negative, we're quite confident that it's the other class. We don't need it yet, but what I've done here is I've written this norm as a function of p. So we get a different norm for every value of p and a different norm for every graph. And let's take the case that p equals 1. I guess that should probably be 2 to the p minus 1. No, that's correct. I can't do algebra. So imagine that this is absolute value. When p equals 1, well, if we have labels in u1 minus 1, we have 1 minus 1, that's negative 2 divided by 2. That gives us 1, so we pay 1 for each cut edge. We're summing over the edges of the graph. These edges we pay nothing for because negative 1 minus negative 1 is 0. Likewise, if we made p2, 1 minus 1 squared is 4, divided by 4 is 1. And so this norm always gives us the cut when labels are in minus 1 plus 1, and it gives us some nice smooth value for all u.
One question. Term on the left, why do you need 2 p's? Why is there 1 p at the top and then g comma p?
Why do I have this 1 over 2p?
No, just on the left where it's like u, like the magnitude of u, and then you have 1 p at the top and then the bottom is
right. So technically what I should, let me write this out. So we're going to generalize it anyway slightly. Good question. So this all makes sense in the context of the class. Let's remember what the properties of a norm are. Okay. So norm has the following 3 properties. One, it has this homogeneity property that you if you multiply it by a scalar, the scalar comes out. So we have the norm of a times x, where a is some scalar, is equal to the absolute value of a times x. 2, we have the triangle inequality. We have the distance on the side, the distance from x, the distance to y is greater than or equals to the distance of x plus y. And finally, 3, we have a unique 0. We have the norm of x equals 0 implies x equals 0. Okay? So what I've actually written down there is the norm to the pth power, because if you observe, we'd have to take the pth root of it, otherwise it's not scaling properly. It's just like, you know, the norm, the 2 norm, we square each of the terms and take the square roots. I didn't want to add another root there, I just wrote it like that. It's a semi-norm. You know, we'll come back to this later, but it's a semi-norm because we have more than 1 0. We don't have a unique 0. Maybe you can think about during break now why we don't have a unique 0. But before we take break, any final questions? Okay, let's take a break for 10 minutes and return and to understand the complexity of graph classifiers.
Ça me...